Section 3.5. We're going to talk about complex zeros of polynomials. We're going to use conjugate pair theorems to find zeros of polynomials, and we're going to find polynomials given zeros. Fundamental theorem of algebra states that every polynomial p of x with complex coefficients, it has at least one complex zero. Factorization theorem says if p of x is a complex polynomial of degree n, where n is greater than or equal to 1, it can be factored in n linear factors of the form, and they're not necessarily distinct. P of x is equal to a times x minus r sub 1, x minus r sub 2, and so forth, where the a and the r sub 1, r sub 2 are complex numbers. The number of zeros theorem says a polynomial of degree n has exactly n zeros, provided that a zero of multiplicity k is counted k times. So if you have a double root of 1, you count it twice. If p of x is a polynomial function whose coefficients are real numbers, and if a plus bi is a zero, then its conjugate, z bar, which is a minus bi, is also a zero. So if 1 minus 3i is a 0, 1 plus 3i will also be a 0. Odd degree polynomials with real zeros. Any polynomial of odd degree with real coefficients must have at least one real zero. And if you remember the end behavior of an odd degree polynomial, the ends go in opposite direction. So if I have an x-axis right there, there has to be at least one zero, if not more. The factorization theorem for a polynomial with real coefficients says that every polynomial with real coefficients can be uniquely factored over the real numbers as a product of linear and or prime quadratic factors. For a polynomial equation with a sub n as being the leading coefficient and a sub 0 as a constant term, the following is always true. The sum of the roots will always be the opposite of a sub n minus 1 over a sub n. Remember, this is your leading coefficient. This is the coefficient that would be right next to the leading coefficient. The product of the roots is a sub 0 over a sub n if n is even. So the constant term over the leading coefficient. If n is odd, it's a negative of that. And also, any quadratic can be written as x squared minus the sum of the roots times x plus the product of the roots, if you're given two roots. So for example, if I'm given 1 plus 3i for a root, you can say, oh, I know that 1 minus 3i is a root. And if I take the sum of that, if I add them together, I'll get 2. If I multiply them, I will get 1 minus 9i squared, which is 1 plus 9, which is 10. So the quadratic that has those two roots will be x squared minus the sum of the roots times x plus the product of the roots. And if you use the quadratic formula to solve that, you better get 1 plus or minus 3i. Find the remaining zeros of a polynomial with real coefficients having degree 3. So I know there's 3 zeros. One would be 2. One is 2 minus i. So that's 2 of them. Now I need a third one. The conjugate is also a root. So it's 2 plus I. It's that conjugate pairs theorem. Find the remaining zeros of the polynomial p of x with real coefficients having degree 6. So here I have 1 root, 2 roots, 3 roots. There's 3 more. So if positive 2i is a root, negative 2i is. If 4 plus i is 4 minus i. And the last one, you might want to write it like this. Negative 1 plus i, because its conjugate is negative 1 minus i. That's what changes, the sign in front of the i. Okay, so there are my remaining roots. Negative 2i, 4 minus i, and negative 1 minus i. I also, this is not in your notes, but here's a quadratic that quadratic factors. And if you solve it, your roots are -2 and -3. So I just want you to realize that if you're given a root of -2, that's a factor of x plus 2. And if you're given a root of -3, that is a factor x plus 3. Okay? So don't forget about that. And again, also the sum and product of the roots. Don't forget about that. The sum, if I had like 1 plus I, the sum, I know 1 minus I would also be a root. The sum is 2. Product would be 1 minus I squared, which would also be 2. So a quadratic with those two roots would be x squared minus the sum of the roots times x plus the product of the roots. So this should be faster than writing it like this. Find the polynomial with real coefficients having degree 4, a leading coefficient of -3, and zeros of 2 plus 3i, 1 minus 4i. So remember that the other zeros would be 2 minus 3i and 1 plus 4i. There are two ways to do this. I'm going to show you the longer way first and then the shorter way. So I could write that polynomial. There's my leading coefficient, -3. And my zeros, I could do x minus the first zero times x minus the second zero, and so forth, and do them all multiplied together. The problem with that, it does take a little longer and you probably will make mistakes. So if you just multiply everything together, I rearrange this, x minus 2 minus 3i, I put these two together, x minus 2 plus 3i, I put that together. So now it makes it easier when you FOIL it, first, inner, outer, last. And I did the same thing here. When you FOIL it, it gets a little easier. When you do first, inner, outer, last, since it's a plus and a minus, the outer and inner will cancel out. So you basically have x minus 2 quantity squared and then minus 3i quantity squared. Here you have x minus 1 quantity squared minus 4i quantity squared. And then just do the math and keep combining your like terms and keep combining your like terms. And you probably need to pause the video to make sure you get it right. But there's everything combined. If you were doing this on a test, or if you're doing it on your homework, stop right here. Okay? You don't need to multiply it all out. And if you need to check your answers, because the answer in the back of the book will be this one, come to my answer book, and I will have them written out like this. Okay? So you don't need to multiply it all out. Just stop right there. But the faster way to do it, in my opinion, is use product and sum. You have the two roots. So the sum of those two roots would be 4. The product of those two roots would be 13. And then that will give you this quadratic equation. So I have one quadratic equation. My other two roots. Find the sum of my zeros and my product of my zeros, the other two roots. And find the quadratic. And now you have your leading coefficient, we said, of -3. So you have -3 times this quadratic times that quadratic. And like I said, stop here with the real numbers. This is fine, stop. But you can see you get the same answer. Example 4. Given a polynomial p of x is equal to x to the fourth minus 2x cubed plus x squared plus 2x minus 2 with 0, 1 plus minus I, find the remaining zeros. There's two ways you can do this. One way you can use synthetic division. One way you could find the quadratic and divide the two. Either way works. I don't care which way you do it. I use synthetic division twice. So my coefficients will be 1, -2, 1, 2, and -2. So you bring down your 1, 1 times 1 minus I is 1 minus I, add, multiply, add, multiply, add, multiply, add, and you have 0. And now from there, my other root is 1 plus I, so do the same thing. Bring down your 1, 1 times, add, multiply, add, multiply, add, oops, sorry, I can stop there. This is where we stop after this, because I went from an x to the 4th to an x cubed to an x squared. So now I have my x squared minus 1 is what I'm left with. And that factors into an x plus 1, x minus 1. So my remaining zeros will be 1 and -1. So, or you could do the sum of the roots, product of the roots, and then do, whoops, long division. Okay? Either way works. I know a lot of you do not like long division, but you could do long division with it. Given the polynomial p of x is equal to x to the 4th plus x cubed plus 7x squared plus 9x minus 18, find all the zeros. So to find all the zeros, you would use the rational root theorem first. So the roots, or the factors of 18 are 1 and 18, 2 and 9, and 3 and 6, plus or minus. And the factors of 1 are just 1. So I'm going to divide these factors by 1, and I just get those factors. And now you can pick 1, -1, whatever you want, and use the use synthetic division. So you could try 1 if you wanted. Here are my coefficients. So bring down my, oops, bring down a 1. 1 times 1 is 1. Add, you get 2. Times 1 is 2. Add, multiply, add, multiply, add, and I get 0 here. So now I started with an x to the 4th, and now I'm down to x cubed. You could try 1 again if you wanted, but I can tell you what, now positive ones won't work because these are all positive, because it's x cubed plus 2x squared plus 9x plus 18. So no positive numbers will work. Okay? So that's what I have right now. So I'm going to try -1. If I bring down my 1, 1 times -1, add, multiply, add, multiply. This did not work. So try another one. So what did I try here? I tried -2. And remember, I'm trying this x cubed. I'm not going back to my x to the 4th because I'm wasting time if I do that. Bring down my 1, 1 times -2, add, multiply, add, multiply, and this one worked. So now there I am. And if I want to find all my zeros, x is equal to 1 is a 0, x is equal to -2 is a 0, and if I were going to solve this one, x is equal to plus or minus 3i. I've solved it. So the remaining zeros are, I have +1, -2, and plus or minus 3i. And I'm done. And like I said before, when you're doing this, when you're at these problems right here, like 19 and 21, you do not need to multiply it all out together. You can just leave it as prime factors.